40%. So that'll be 39.4%. Is everybody with me? A little under 40%. So almost 40% of the behavior in the dependent variable can be explained using the independent variable. Is everybody with me? Okay. Yes. Thank you, brain. Okay. Family Feud, when they ask you a question, top 5 answers, and you know how they put point values on them, and the more popular answer has the most points on them, right? They could visualize like the Family Feud board and like like the top 5 answers. And even so, when those points don't always add up to 100, right? So it might add up to like 97 points. You get them all, you get 97 points out of 100. So there are 3 points unexplained that's unexplained in that question. You understand? Some other. You understand? Does that make sense? Mm-hmm. So there's 60%, almost 60% of unexplained variables. You see what I'm saying? That can help explain the behavior of episode total. Now, if you want to try to capture that unexplained behavior, you need to add another variable to the model. Is everybody with me so far? And see if it'll capture more of the variability. Does that make sense? Because right now you've only captured a little under 2/5 of the behavior in the response variable. Okay? And the higher the coefficient of determination gets, the better your model will accurately predict. Okay? It'll predict really good. Your question.
I was gonna say because it's 0.62, there's evidence, but because it's not 0.7, you would say there's not strong evidence.
Right now you would just say fairly strong evidence. But of course, the best way, the formal way of saying if this is significant is to perform a hypothesis. See, right now you can say this shows fairly strong evidence. Okay, fairly strong evidence. But I'm gonna tell you, it's this that we're gonna be talking about next. This says it's significant. Okay, we're gonna get to that in a moment. So hold tight on that.
Professor,
right. Yeah, go ahead.
I clicked on the error on that one.
Here?
No, the error down on the bottom right.
Oh, right here?
Yes. Would that be considered the model or?
Right. That is this is the regression line, the regression model. And that is, let me do it this way. So that is the best fit line. We call it the least squares regression line that explains this data. And that line, the equation of that line is right here. It's right there. It's these two numbers right here. So that's the constant and that's the slope. So we're going to talk about that. That's coming up. So you're in the future. Everybody loves going to the future. This is good. This is good. Really good. All right. So getting back to the PowerPoint. So like let me remind you, correlation does not imply causation. Okay. So you cannot, when you write up your findings, you can't say that increases in episode total are due to the number of pricing games won. Is everybody with me so far? You can't say that universally. All right. You can conclude that. You can say that there's a high association, a high correlation, but you can't say that. You know, if you want an episode to win more, you have to win more pricing games. As you can see, it could be that could be true, but there are other factors. You see what I'm saying? And you never know. There could be an instance where you won 5 games, but it was still a low scoring episode. Is everybody with me so far? So you have to be careful not to say that one variable causes the behavior of another variable.
It's the same thing as saying because of.
Say again?
Like you couldn't say because of.
Right.
Okay.
Right. You can make a conclusion that that the association is strong between those two variables, but you want to avoid saying that this happens because of episode episode total is it increases because of the number of pricing games going. You want to avoid doing that. Yeah. All right, moving on. Now we go into the third case, model. Okay. Model. So now that we see that there's a linear association, we can see it. We have quantified it. Now the only best thing to think about is, well, if I know the value of one variable, can I use it to predict the value of another? And notice what I said, to predict, okay? So when we made that model, it doesn't mean that that model will always tell what will happen. It is predicting what will happen, okay? That's what regression models do. They make predictions, okay? So we're gonna make a regression model, and I'm gonna show you I showed you how to use it in StatCrunch. It is important to note that regression models are used to predict and not guarantee, to provide truth. Now, we want models, don't get me wrong, there are some models I've seen where for some cases, it predicted perfectly. And for other cases, it was off by a little bit. You see what I'm saying? We want models to predict fairly well, but they're never going to be pitch perfect where it predicts perfectly for every case. Okay? So, now, here is, this is called the least squares line, regression line. And it's just like MX, look, it's just MX plus B, y'all. But instead of statistics, we use B naught and B1. B1 is like the M, the slope. This is the slope, and this is the coefficient. This is the constant, or the intercept. So in statistics, we put it backwards. We put the constant first, and then we put the linear combination part second, the slope and the independent variable second. I'm not gonna cry if you had it the other way. I'm just saying this is our custom in statistics. We put the constant first, then the slope, and then the independent variable. Okay, and then notice that we use y hat. This hat means predicted. That little hat on the y means predicted. We can't say y because, like I said, this is used to make predictions, not necessarily truth. Okay, so we call this the predicted response value. Okay. But that is the independent variable. So we're trying to predict the y value given that we know the value of x. So for our example, we're trying to predict the episode total, given that we know how many games were won on that episode. Is everybody with me so far? So, all right. Keep in mind that these are statistics because they're calculated based on the sample. They are estimates of their population parameters. These are the population parameters, B naught and B1. Beta naught and beta 1. This is the population intercept value, population constant. And then this is the population slope. These are estimates of that, right? All right. So when we use StatCrunch, we're creating this equation. Is everybody with me? I'm just giving you a quick background on this. So you don't really need this. This is what you need the most. Okay? This is the y-intercept, that's the slope. All right? All right. Now, these are the formulas that are used to calculate the intercept and the slope. Okay? Now, let's do a quick recap really quick. We just talked about that. That's correlation coefficient, right? What are these? Let's go down memory lane. Now that we're getting close to the end of the semester. What was S? What was S? First of all, it's an alphabet. So what's the first thing you're supposed to say? Sample. Sample what? What was, say again? Standard deviation is the correct answer. This is sample standard deviation. But that's sample standard deviation of the Y data. Because remember, we had two columns of data, right? We had episode total, which was the Y data. And we had number of pricing games won, which was the X data, right? So this says calculate the sample standard deviation of the Y data. And then this is calculate the sample standard deviation of the X data. So you can, and then of course you can make StatCrunch do that if you have a large amount of data. So you can calculate the slope. Once you get the slope, you know this value, and then this is just what? What is this? That's just what? Sample mean, right? Of the X data, right? This is the sample mean of the Y data. So you can calculate the constant, and then you know the equation of the regression line. Now, if you don't remember these, you can still calculate slope, but you gotta use this form. Now we gotta go back to the Adam and Eve. We need the summations. You see that? You would need the summations. So you can calculate slope even if you don't remember how what these were. You can calculate slope by using those summations, those five summations that we did. Okay? And then similar for the constant, for B naught. You can calculate the constant if you know the 5 summations. Okay? Now, for regression, we tend to round to, it's custom we round to 3 numbers after the decimal point. Where is it? Yeah, underline this. That should have been underlined. 3 numbers after the decimal point. So when you get these estimates, you should round them to 3 numbers after the decimal point. Whether if you did them by hand or if you do stack crunch, use stack crunch. So I showed you how I calculated them. I used I did the advanced way. I used the sample standard deviations, correlation coefficient and stuff. And then I got the equation. Okay? And then that should be the same as the output from, that should be the same as the output, see, there it is, see, 38.439. So here, 38.439 plus 18.357. Is everybody with me? X. Because that's the slope, so that X. All right. All right. What else I was going to show y'all? Yes, I know. So now you see where these estimates are in the output. They're right here. Okay, they're right there. These. All right. Going back. Now that we have the regret, so here. Before we do that. Let me write that up on the board because now I'm leading into something. So we said y hat is equal to 38.439 plus 18.357 x. And again, where y is episode total, so this is, but it's y hat, so it's predicted episode total. And then this is the number of pricing games won. I'm putting that up on the board because now I'm going to go back here. Why do we create a regression model? We want to predict. So let's say that they were going to make a 189th episode. They haven't aired yet. And we want to say, well, on average, they win, their 3 pricing games won. I want to now predict how much will be the total amount won. I want to predict that. Total amount won at the end of the episode. So what I would do is, I want to say, well, what is the predicted? So I'll put it right here. What is the predicted episode total for a show that had 3 pricing games won. So what I would do is I would plug in 3 into this and for X. Is everybody with me so far? So that would be, so it'll be y hat is equal to 38.439 plus 18.357 times 3, and then whatever that's equal to. So, I'll switch back. So 38.439 plus 18.357 times 3. I get 93.51. But you're not done. 510. But you're not done. You have to interpret this back in terms of scenario. Remember, what was the, it was by the thousands. So we have to multiply that by 1,000. That's just moving the decimal place to the right 3 spaces, right? So that's going to equate to a predicted amount of $93,510. Is everybody with me so far? Now we only have to do this because the y values, the dependent variable values, they were rescaled to be per $1,000. So remember, that's the predicted amount. Now, if that episode were to air, and 3 pricing games were won, and let's say the total amount was $93,510, this model predicted perfectly, right? Let's say, however, it was a grand total of $92,000 won. Then this model overestimated because the predicted value is over the actual value that actually happened. Is everybody with me? So for that case, it would have overestimated. Let's say that the episode, there was they did well, 3 pricing games were won, but the grand total for that day was $100,000. Well, then the model would have underestimated. Is everybody with me? The predicted value is under what actually happened. Is everybody with me so far? So sometimes the model will overestimate and sometimes it will underestimate for certain cases. All right? And of course, the difference between what actually happened and what was predicted, that's the error. That's the error in the prediction. Is everybody with me so far? All right. Now, the slope is interpretable. This slope is interpretable right here. And actually, for this scenario, this value is interpretable. Okay? Let me first say this. The slope is always interpretable for a regression model in terms of the scenario. Always interpretable. For every game won, for every one pricing game won, the predicted or the expected, for every one game won, we expect, this is what I said, we expect the episode total amount to increase by $18,357. So what this says is that, a little over 18,000. For every pricing game won, expect the episode total to increase by $18,357. Now, this one, the intercept, sometimes, depending on the scenario, sometimes you can interpret it and sometimes you can't. Okay? You can interpret the intercept if it makes sense to plug in a value of 0 for x. For this scenario, can we plug in a value of 0 for x, yes or no? Yes, because we saw, if we go back here, where are you? There you are. If you go back, there were some episodes where none of those contestants won their pricing games. So 0 makes sense. Can I interpret the value of 0 in terms of the scenario? The answer is yes. X equals 0 means none of them won their pricing games. Is everybody with me? Therefore, I can interpret this value. So what this value says is, if nobody wins their pricing games, expect the episode total to be somewhere around $38,439. Is everybody with me? Sometimes you can't interpret this. It all depends on, can you plug in 0 for your independent variable? If the answer is yes, you can interpret this. If the answer is no, you do not interpret that. Okay? Because if you interpret it, you're going to look like a damn fool. Because they're going to be like, well, 0 doesn't make sense. Why would I use this model for 0? So why are you interpreting that? Is everybody with me so far? All right. Questions so far? You either constipated or you understand. Okay. I'll talk to you. Now, you see that little analysis of variance? I'm gonna tell you right now, I love this. Okay. When we go to chapter 11 and we cover one way ANOVA, we're going to talk about how to do ANOVA table. There's an ANOVA table for regression. I'm going to tell you right now, you don't need it. You don't need it. We don't need it for this case. Because look, I'm going to tell you a couple of relationships. Your observed test statistic, if I want to determine now, is X a statistically significant factor to predict Y? The answer is yes, because the p-value here. But that's the observed test statistic right here. Okay? And see, all this is just a repeat of this. See, this 120.962 is just this squared. You square t, and you get this f. Okay? And then this p-value is going to be the same as that p-value. So right now, we don't need any of this when we do linear regression. So you don't need to know this. But the next chapter, when we cover one way or another, you will need to know this. So we'll get to it when we get to it. Now, here's one more thing, just so you know. There's some nice patterns about this table. The values add down and they divide across. See, look, 1 plus 186 is 187. This plus this is this. Is everybody with me? And then they divide across. Look, this divided by that gives you this. This divided by that gives you this. And then one more pattern. The ratio of this. This divided by that gives you that. We're going to learn that. Don't worry, we're going to learn that. That's the next chapter. Those three patterns are very helpful. Okay? So if you're doing, I say all of this to mean the following. If you end up doing a regression model for your project, the only piece that I need is this. Okay? This table and this output. Is everybody with me so far? That's what you would need to provide. All right. Now,